Hello, sir.
Yeah, hello Pratham, I'm audible.
Yes, sir.
Okay, so yesterday what we discussed,
Capacitance.
and I'll just share my screen. Okay, today we can start with some new topic, which is from where I ended yesterday. With some country, electric. We covered parallel plate capacitor, Pratham. Hello.
Yes, sir. Yes, sir. Yes, sir.
Have we covered the parallel plate capacitor?
Yes, sir.
Okay, electric potential for the parallel plate capacitor. I covered. After this, we don't have any utility. So today what we can cover? I think I must have told you some topics to be discussed in today's class.
Yeah,
Correct?
you told three or four.
Three or four?
Yeah, the last topics about they were about capacitance only.
Okay, I was talking about the capacitance only. Alright, so maybe capacitance. mm,
Have we done equivalent capacitance?
Equivalent capacitance. Okay, we have to. I think I told about the circuit related to capacitor, right? Maybe those kind of things.
I think yes.
Yes, okay, no problem. Okay. What I could remember, we covered force on a in between capacitor, right?
Yes, we are.
Okay, fine. So let me check if I have some problems, so we can solve some problems and then we'll move to the next thing. Yeah. Okay, let's talk about topic loss of energy during redistribution of charges. Redistribution of charges. What does this mean? We'll tell you later. Okay, I'll just tell you. For example, you had two bodies. Okay, two conductors. These are two conductors. And right now, these are uncharged. Okay. You know, to make parallel plate capacitor, you need positive charges this side, negative this side. So what we can do so that we can make a parallel plate capacitor out of this? Any idea?
What we can do to make a parallel plate capacitor of the that?
Yeah, yeah, like what's any idea like what we should do so that I can make a parallel plate capacitor out of these two plates? Okay, I
We'll
have
induce
one.
one side with negative or positive charge.
So one thing I we can do is bring a positively charged plate. Okay,
Yeah.
and put it in front of negatively charged plate. What will happen? There will be induction happen, and this plate will get induced with negative charge. So we can say
Yes.
there is some inside kind of capacitance will happen. Another way you can do is just keep it like this, okay? And connect one battery. Clear?
Yes.
This battery from this battery, the current will flow until this potential becomes equal. Okay, you know how the potential becomes equal, right? What happens? From here, some charges will be flowing. Okay, some charges will start flowing. As more charges will be accumulated at this point, there will be increase in potential. Okay, and you know, like increase in charges will be there, and you know, more charges are there, more potential is there, right?
Yes.
Until when they are going to be happening? Until this capacitor has potential equals to V, equivalent to V. Is that clear?
Yes.
Okay. Now, similarly, we are going to study another thing. Let's keep it here. Now we are going to discuss. Just assume you have two capacitor. Okay, one is C1, another you can say C2, something like that. We are going to charge both of them separately. So take two capacitors, C1, C2, charged up to V1 and V2 potential separately. Separately mean to say they are independent. Okay, separately. So figure if I have to make, this is C1 capacitor charged up to V1. This is C2 capacitor charged up to V2. Is that clear? So if I
Yes.
ask you what is the charge stored in this capacitor, you can say Q is equals to C1 V1, and in this one I can say Q2 is equals to C2 V2, right? Can I say
Yes.
this? Okay, let's see. Now what my task is, I am going to connect these two capacitors. Okay, how I am going to connect? For example, this is the positive plate. This is also the positive plate. I am going to connect positive plate of this capacitor to this. Should this should make what I'm going to do. I'm going to connect this. How I'm going to connect positive with positive. Let's connect these two capacitors with positive of C1 to positive of C2, and so on for the negative also, for negative plate. Okay, so if I do this, then what will happen? It is going to this part and it is going to get connected with this one. This is going to get connected with this one. Clear?
Yes.
After this, what will happen? It will look like this. This is your C2. This is your C1. This is initially what is V2, and you can say V1. So this is initial configuration. Okay, initial. What will happen after connecting? After connecting, okay, just assume it. You can now, if I ask you, it's isn't it acting as a simple connection? For example, isn't it looking like you have two batteries, V2 and V1, right?
Yes.
So what will happen? There will be some charge flow will happen. Why happen? Because of the difference in potential.
Okay.
Okay, so this there's some charge will be flow. Okay, charge will be flow until unless potential on the both becomes same. Is that clear?
Yes.
Why we are considering for the same potential, even though they have different capacitors. Just assume I'm just taking another example. Just take this example, a bigger tank. You can see this is bigger tank, this is smaller tank, right?
Okay.
If I have water till here, just assume I have water till here in this, and I have water till here in this, right? So which has higher potential? You know that it has higher potential. Can call as MGH, can call as MGH, right? If I just connect it with this tank, what will happen? Even though this has much more water than this, right? We are not considering about the how much water it can contain or something. We are considering about the net potential it has. Okay,
Yes.
okay. You can see if I say this area is just 1 meter square. Okay, and this
Mhm.
is height is somewhere around 10. So the total volume, how much is this? 10 meter cube, right?
10.
And if I say this volume is itself your, like this area is itself, you have what I can say, 100 meters square, right?
Yeah.
And length is also the same. So total, you can see if this length is 1 meter, still the water is much more than this. But still water
Yeah.
will flow from this much this to this. Is that clear? Why this is happening? Because of the higher potential. It has higher
Yes.
potential. it will flow
Okay.
until this will get increased such that, although it will be very minor, you can't even see because the volume part, it will go like this, and water in this will get decreased until the
Yes, sir.
levels get same, something similar to this. Right now you can see
Yeah.
the flow will stop. Okay, the flow will
Mm.
stop. So same is going to be here.
Okay, sir.
Same in this case also. So the charges between both capacitors will flow until potential becomes equal.
Yes,
Until
sir.
potential becomes equal. Okay. So just assume the final potential will be something V, right? Because they have to be equal.
Yeah.
And one more thing, the charge is conserved. Is it?
Yeah.
Oh, sorry. Like charge is conserved. Huh? If it has Q charge, Q1, it has Q2 charge. Right?
Yeah.
So the total will be Q1, Q2. Q1 plus Q2. Doesn't matter, out of this Q1 minus X goes to this much. Like it can happen that from here X charge, let's say X charges go from here to here. So it will become Q plus X, it will become Q1 minus X. It can happen. But the net will still be the Q1 plus Q2 because we are not giving any source of energy from which charge can go somewhere else, right? It's just an isolated body. So can I say
Mm.
what is the initial charge? We have to do just charge consumption. What is conservation? What is
Yeah.
initial charges? Q initial is
Q
equals to
initial.
Q final. Right? What is Q initial? C1. Okay, write
V1.
it like this. Q1 plus Q2. What is Q1? C1 V1
Yeah.
C2. Clear?
Yeah.
Finally, also, what is the final? It should be again Q1 dash plus Q2 dash.
Okay.
What is final potential? I told you the potential of both are same in this case. VV. But you know that capacitance is an internal property, it won't change. So it will still be like C1 V1 dash plus C2 V2 dash. And what is V1 dash equals to V2 dash? That is equals to V. So can I write this as V equals to plus C2? Can I say this?
Yeah.
Okay. So what is final potential? That is this much. C1 V1 plus C2 V2 divided by C1 plus C. Is this clear till here?
Yeah.
Okay. Now, the what was the topic? The topic was loss of energy, right? How much
Yeah.
energy has been lost? Just assume we don't know whether the energy has been lost or not. You know one thing, to get any change, what we do, we calculate final minus initial. So we are doing the same. If if final minus initial is positive, it means final is greater, initial is lesser. It means we have gained something. If you do just if final minus initial comes out to be negative, it means final is less, initial is more. It means we have lost something. Is that clear?
Yes.
Okay. If somewhere it is written that we have to calculate loss, so you have two options to do this. Just do final minus initial. Whatever you are going to get negative, it means you are having loss. Another is you already know I have to calculate loss. It means I should check I minus F and it should come out to be positive. It means it is that clear?
Yes.
Okay.
Clear.
So I'll just remove it and let's calculate the energy. So what is the initial energy? If I ask you what is the initial energy?
QI.
Yeah, so that is UI. What is that initial energy? And if you see initially we had both as separate entity, right? C1, C2. So I can calculate separate energy. What is the separate energy? Half. You can say Q1 square C1 plus half Q1. You can call it as Q2 square by C2. Can I see this?
Yes.
Okay. What is final energy? Half times of C1 plus C2 multiplied by V.
Okay.
Okay. Also, It's up to us, like in which equation we are interested in. So you can also rewrite the same thing, this particular thing, as a half C1V1 plus half C2V2. Clear?
Okay.
Yeah, you can write
So
this
same thing.
as, yeah. Okay, what is value of V? We have just calculated this. So can I say it is nothing but uh,
C1 V1 plus C1 C2 C2 V2.
okay, it should be square. Wait, I just made a mistake. It should be square, okay?
Okay.
Half CV square was the formula, right? So it should be
Yeah,
square.
yeah.
So this will also become square. This will also become square. That's why I just. Okay. Wait a second. Remove it. Now we have to just convert the equations. How we can convert this? Either convert this into Q in the Q form, or from Q form to this form. You have two options, right? So what is
Yeah.
the best option we have? If you see, this V is my total potential, right?
Yes.
Or in another sense, what I can say, can I write instead of this something else? Wait,
I don't know.
okay, wait. Can I write instead of this whole thing Q1 plus Q2 square divided by C1 plus C2? If you see, this thing is something, write this, right? If I just say that, remove it as a single entity, can I call this as a single capacitor? The how much charge is having the single capacitor Q1 plus Q2, and what is the net charge, net capacitance, that is C1 plus C2? Is it
Yes.
okay? And if you see, the potential is also in the parallel sense, right? Is parallel. At this
Yeah.
point is V, at this point is zero. So we can say this V square thing can also be written as CV, right? So V can be written as Q by C. So what you are going to get from this equation? From this, if you just put V square equals to Q square divided by C square, what you are going to get? This thing, okay? So I'll just remove this for a while. So from here, we can get directly half Q1 plus, okay, I have already written, right? Already written is there. Now
Yeah.
what I have to do? I just have to do final minus initial, or basically you just have to calculate change of
Yeah.
u final minus u initial. So if you just solve this, half, this is half, this is half, this is half, I can take it out as common. I left with, okay, final minus initial I have to do, right? Okay, let's do final minus initial. So q1 plus q2 square, remove it from here, c1 plus c2 minus, what is the next part, that is q1 square plus by c1 plus q2 squared by c2. Clear? Just simplify the equation. If you just try to simplify the whatever the equation we have, we can get something like delta u. Okay, in the denominator I'll be having 1 by 2 c1 plus c2, c1 c2, I'll be having c1 plus c2. Okay? Now if you see, we can just take all these things as we have to solve this part, right? How we can
Okay.
do this thing? It's simple. Just q1 q2, no, it's just one more plus is there, square c1 c2 minus q1 square with c2 plus q2 square c1, and both thing along with c1 plus c2. Is this clear? Just check the LCM, and this LCM
Yeah.
portion we have already written outside.
Yeah. Okay.
Just check it once and let me know is it correct or not.
Yes, sir.
It's right, right?
The
So in the next we can write it as, look, the next part is you have just have to expand this thing, okay? If you expand this one, what you are going to get? Q1 square, there's c1 C2 plus Q2 square C1 C2 plus 2 times of Q1 Q2 C1 C2. This is
Yes.
subtraction, so whatever we are I'm going to write, I'll put this subtraction. Okay, so this Q1 square C1 C2 negative. Okay, another
Okay.
Q1 square C2 is there, and that another C2, so it will become square. Put negative also. Q2 square C1 square negative minus Q2 square C1 C2. Just look at this and let me know, is it clear or not? Clear, right?
Yes, sir. Yes,
Okay.
sir.
If you see carefully, delta U becomes half 2 C1 C2 C1 plus C2. What I have left in numerator, that is 2 times of Q1 Q2 C1 C2 plus minus actually, or you can say just put negative like this. Q1 square C2 square plus Q2 square C1 square. Is it?
Yes.
Okay. If you see, can I take C1 C2 common?
C1, C2 common.
Or yeah. Okay, let's take C1 C2 square as a
It
common. If you,
the formula for A plus B whole square. A
mm,
minus B whole square.
yeah, the formula is there, a minus b whole square.
But will it be of use?
Okay, basically we wanted to make that and in final. Okay, let's make it earlier also. So let's take this negative common outside. Okay, if you
Yeah.
take the negative at the finally common, so it will become what?
Q
Maybe
plus
Q1
Q2.
C Q1 C1 minus
Acha,
whatever. Like it's up to you. We can say
Q2
anything.
C2. Q2 C1.
Yeah, it will be Q2 C2 whole square. Okay, and what we are left with 2 C1 C2 C1 1 plus C2. So this is the formula of change in potential.
I think it
Okay.
should be Q1 C2 minus Q2 C1.
No, like it is in a square, right? It's the same thing. Doesn't make sense. Like it doesn't make any difference. Okay. Look, a minus b whole square equals to b minus a whole square. The reason is if you if you just take minus common from here, what will
No,
happen?
no, no,
It
no.
will
I'm saying like Q1 C2, not Q1 C1.
q1 c2 and q2 c1. Is it?
Yeah, I'm saying
Wait,
that.
let's see. Was I left with this thing or something different? Okay, okay. Fine. So we can write it like this. Now it's fine.
Yeah.
Okay, so yeah. So this is the formula for your change in potential. Okay, if you see the whatever I am getting, that is negative instance, right? It means this is a loss.
Okay.
Negative, it's loss. Another thing, if you could have startingly assumed that you are going to get loss, then you will be starting with where's the thing? You will be starting with it means you have got what you wanted. If you have got negative, it means whatever you wanted, you have got opposite of that thing. Is that clear?
Okay, sir.
Okay. One more thing, its simplified version is the simplified version of this thing is C1 C2 divided by C1 plus C2 to V1 minus V2 square. This is the simplified version of this thing. Okay,
Okay.
that is basically the simplified version
Yes.
which we can get from this particular equation. We could have got this equation if we could have taken C1 C2 square as a common. If you take the C1 C2 square common, what will happen? There will be one C1 C2 here
Yeah.
at this position. Okay, and yeah, at this point you will be having C1 square, C1 square. Here you will be having C2 square. Okay, and you know what is
Okay.
Q1 by C1? That is V1, right?
V1.
So this formula will be looking like V1 minus V2 square. Okay, you can see the
Okay.
same thing happen. And here already I have one C1 C2. If I have taken C1 C2 square as a common, so one will get cancelled. Okay, so you can see you are
Yes.
getting the same thing in the same sense. So let's simplify the thing. Okay. Maybe. So what is the final value we have got? Two formula you can write. One from this part itself, one from here itself. What it can be? Q1 C2 minus Q2 C1 square
Yes.
divided by C1 C2 C1 plus C2. Okay.
Okay.
Another you can write it as minus um, V1 minus V2 square C1 C2 divided by C1 plus C2. Also,
Okay.
is that clear? So these two formula
Yes.
you could remember. This is a loss of energy in charge distribution. So I'm giving you one problem based on the same thing, whatever we have discussed here. So at this point we can have which this is the first question for the today's class. So given two capacitors C1 and C2, okay? Assume C1 can be called as greater than C2, charged at same potential, same initial potential. You can call it as potential and call it as potential difference. Sort of thing. Now, the charged capacitors have been removed from the battery. From the battery. Okay? Then what we can say? And the plates are connected. Plates are connected. Configuration I will just make below. Let's say this is the configuration. C1, C2. Two charges are two capacitors are there. This is switch one. This is switch two. Okay. Point A, point B, A and call initially this is a charge one, Q1 initial. Call it as Q2 initial. Okay. This is the thing initial.
Okay.
After okay, this is the initial. Whatever the question is here. Then after the switches are closed. Whatever the S1 switches are there, they are closed. Okay. Then what will happen? First thing you have to figure out potential difference between A and B after closing switch. Okay, closing switch. And this B part of this problem will be yeah, energy. Basically, you have to calculate total energy before energy stored in capacitors before and after. Before and after. Switches are closed. Okay. Any other case which can happen in this? These two cases. Okay. Any other question can be framed? Yeah. Third, ratio of final to initial energy to initial. Question clear?
Yes, sir.
Okay, it's a long question. Do you want to try it now or as a homework part?
I think I'll do it as a homework.
Okay, it's good if you do it as a homework. Maybe I can give you one more problem, right? It's better. Okay, let's not do one more. I'll give it to you after if you solve this one. I'll just explain the combination of capacitors, okay?
Okay.
So let's do the combination of capacitor part. Combination of capacitors. Um, for this one, I'll just give you a hint. Solve this question as a part wise, okay? If you solve part portion, you will get the answer for this one.
Okay, sir.
And if you see, I don't think I have given you some variables. You can assume some other variables, and final answer
Okay.
will be in that particular given variable.
Okay, sir.
Look, so combination of capacitors. Okay, are you aware of the resistor combinations?
Yeah, yeah. Series and parallel.
Yeah. So we have two kind of combination for capacitors. One is series, another is parallel. Two main thing is there. In series, we know that current is constant, right? Current is same. And in parallel, potential is same. Is that clear?
Yeah.
So let's figure out the equivalent capacitance in both conditions. The first condition is given as series. If I have some capacitors in series, C1, C2, C3, C4. Okay, so
Okay.
this is given. Yeah, wait. So this is given C1, C2, C3, and C4. Right. In this case, although I know the direct relation also, but I just wanted to do a short derivation. This is the two terminals. Okay, I wanted to
Yeah.
calculate what will
Actually,
be.
the derivation happened today only in class. So
Okay, it
I know
happened,
that.
right?
Yeah.
Okay, so instead I can directly write
Yeah, yeah.
CA will be nothing but, okay, it is different. It should be 1 by CAB equals to 1 by C1 plus 1 by C2. Clear?
Yes, sir.
So I can instead write this CN will be better. For resist for parallel, A is there, B is there. We have two terminals. Out of this, we have some cases. So on. So what is the equivalent of here? CAB
So,
equals to C1 plus C2 plus C3 and so on. C. If you see, it is just opposite of the resistance. In case
resistance.
of resistance, we see this kind of thing in series and that is in parallel. But here the
Yeah.
things get different. Okay. Energy. Let's talk about energy. And how energy will look like in series combination. U equals to, mm, should we do parallel first or okay? Let's do this one itself. Yeah. So what is the energy? If I ask you energy, it is nothing but the total charge, or you can write directly like this, because energy just depend upon how much charge you have and how much potential you have. Okay. So if you are
Okay.
in the series, in series charge is same, is it?
Yeah.
Because in capacitor we don't talk about current, we talk about the charges. So 1
Okay.
by q2 square c, c3 and so on. If you see, okay, just if you see, we can just simply write, we can take half q square common. We can write this one as 1 by c1, 1 by c2 plus so on. What is this? C. So can you see, like we can just write this thing as half q c equivalent, is it?
Yes.
We just okay,
Yeah.
not c equivalent basically. This denominator c can be replaced with 1 by c equivalent because the whole thing is equal to 1 by c equivalent. Energy in the parallel. Look, when we do these kind of problem, we have to figure out which thing is common in the particular case. For example, in parallel, my voltage is constant, so I'll be taking energy in the form of voltage. What is that? Half C1 V1 square plus half C2 V2 square plus half. Okay, V is same, right, for everyone, so I'll be writing this.
Yes, sir.
And so here we can make something like C1, C2, C3, so on. Charge is same. Here we have the thing in parallel. Okay. So you can see again I can take this to b square common. I'll be having c1 plus c2 plus c3 and so on. Can be written as u equals to half v c equivalent and square is there. So you can also write this as half c of equivalent v square. Clear?
Yes.
I don't think you will be having any doubt at this point.
No, sir.
Okay, let's just find out. Okay, one more thing. I'll just give you some configuration note. If you see one this kind of configuration, okay, let's say this is your positive terminal. This is negative terminal, right?
Yeah.
Another is connected with this positive terminal. This is another negative terminal. This is
Mm-hmm.
positive terminal. This is negative terminal, and so on. Okay. This is connected to one some battery or something you can say. Maybe a capacitor having bigger charge equivalent to all things. This can also
Okay.
happen. So if you see carefully, I can say this plate has charge Q.
Mm-hmm.
Just we can say this plate has charge Q. This has minus Q. This plate has again charge Q. This has minus Q. Q minus Q. If you see carefully, this is a neutral thing, right?
Okay.
This again comes up to neutral.
Yes.
That's the reason this has zero charge, this has zero. What is the final charge you can see? Outer and this. So that's why we are saying even though we have the lot of equivalents, lot of capacitance, we have just single charge to be which we can notice. Okay.
Okay.
Because the all the internal charges get neutralized by the negative and positive of the first and another one. Any doubt till here?
No, sir.
Okay. Hmm, what we can have? Okay, so I'll just give you one problem type of thing. Special case basically we'll be studying, not that special. Two capacitor in series. Okay, take this as your homework. Okay,
Okay.
same for the one parallel for the both thing you have to take. You have given something like this configuration.
Mm-hmm.
C1, B1, C2, B2. Bigger is this. Okay, that's the thing. This is what you are given is you have to calculate individual C1, C2 and all.
Okay.
So this is the potential you have given. You can see I have given you V1, V1, V2. So you have to get the proper V1, V2 value. Okay.
Okay.
Same in case of capacitor also. In case
Okay.
of parallel also.
Sure.
In a parallel you have one L here. This is the V you have. Okay. C1, C2. So you know potential is same. So here you have to get the value of Q1, Q2. Okay. So this is your task.
I need to find V1, V2, and Q1, Q2.
Yeah, in two different cases. Okay. This is in the series. This is in the parallel. So
Okay.
basically, you have three problems to be solved as your homework. One this, one another this one, and these
And a
and
question.
this bigger. Okay? This has basically three problems in itself. Any doubt?
Okay. No, sir.
So this is all for the today's class. Okay, if you have any doubt,
Okay.
let me know, or else these three problems as your homework.
Okay.
Clear? So yeah, we can end
Yes,
the
sir.
session by here.
Thank you, sir. Bye,
Okay,
sir.
goodbye. Bye.